So the next speaker is Angram, who is going to talk about OCaml Insight, libtls, a drop-in replacement for libtls. Thank you. So my name is Angaron and I'm gonna present you the project I worked on during my internship at the University of Cambridge, which is a libtls drop-in replacement for libtls. So what is libtls? libtls is a C binding to OCaml TLS that aims to be fully compatible with libtls, which is a library, an interface for OpenSSL that came of the libsSSL project, the OpenBSD's fork of OpenSSL. And I'm gonna start by showing you a little demo of it. So we're gonna basically take a look at the library running using within HTTPD, OpenBSD's HTTPD. So to get started, we'll just start the HTTPD using the regular libtls library. Oh, not working. So the daemon started, and we're gonna try to load a video available on server. Oh, we lost the thing. Too bad. Give me a second. So we have here a video that will load through HTTPS. So this is still the original OpenSSL video running, and now we're gonna replace it using our library. So we will stop the daemon. We can see in the code on the left pane that we added a little print line to show that this is the actual OCaml library running. So if we started by there we are. So we can see that this is the actual OCaml library that run within HTTPD, and if that to run again the video. It will load as normal. We can scroll through it. So encryption is happening in OCaml, but the connection is not quite alright because the certificate is not valid. It's a custom create one, so it's not amazing. But yeah, here is the video running through our library using OpenBSD HTTPD. I don't think I can show you anything as evident as this. Quite hard to show you that the OCaml library is running, so just trust me if you want. This is actual OCaml code, and now we're getting back to the presentation. So now we can try to think about what are the challenges in replacing a system library. What I mean by a system library is taking a traditional C system library, which is like, for example, OpenSSL that you will use to start TLS connections through your web browser or any daemon. So one of the challenges are obviously the most evident one, that most libraries are written in C and used by C programs. In any traditional Unix system, you actually, well, every programs and libraries communicate using C. So this is the first problem. From this problem, we move on to even more problems. That is, for instance, if we try to change this library using another one written in another language, we hit some new problem, that is memory management. C being programming language where memory management is actually manual, we hit the problem where OCaml is, for example, a language that has a garbage collector where memory is automatically handled by the garbage collector, and a few other problems like languages, idioms, where basically C is a very imperative programming language and OCaml is more of a functional one. Other problems arising from this kind of plans is also those switching to another programming language introduce important performance loss. C libraries are usually very fast, so that's the kind of question we'll try to answer with this project. So to get back to libtls, libtls is a C binding to OCaml TLS, fully compatible with libreSSL libtls interface, which is a new interface that started maybe 2 years ago, I don't remember, that is starting to get widely used into OpenBSD's base system. It's an interface that aims to be leaner and simpler to make a developer's experience simpler and less dangerous, I say. And libtls use almost no manually written C stubs, thanks to OCaml C types inverter stubs. So OCaml C types, to do a little reminder of it, is a library that allows you to express binding to C libraries using OCaml functions. So in this example, we have a TLS server function that will initialize an empty TLS context and will just return some pointer to the TLS value we just created. And right next to it, you can see a function call to iInternal. I is a module of C types, and internal is a function that allows you to register a binding. Here it's to some TLS server symbol that will be the final name of our C function. That is a function that takes no arguments, which is void, and in OCaml terms will be a unit, and that returns a pointer to some TLS types. And the function that will be called back when the C program we call it is the TLS server function we define just up here. And the generated C code looks pretty much like it. So the interesting part is that we managed to replicate the C signature, which is struct pointer to a struct TLS server that takes no argument, and then the automatically generated OCaml code will do the necessary wrapping to make the call to the OCaml code happen. So now, what does that mean to actually replicate libtls interface when getting from the OCaml code? So here is what I'd say is one of the entry points for OCaml TLS. So those two functions allow you to pass some configuration options and get some TLS context. The two main functions will be then the client function and the server function. So that's pretty common OCaml code. That means that, well, you pass around some types that are well defined. You have a few arguments that are optional or not. So that actually means that those arguments can default to some values that the library decides to, and you know about it. And then it takes a unit to just return either a client or a server. So getting back to libtls, it more looks like something like this. So it's quite a complex interface where in the C style, you first start to get the configuration struct that you need to free later on, and then you have a few dozen configuration options that aren't quite obvious on their semantics, because basically a nice difference is that you don't know which ones of the function actually have default values in the configuration structure, and some other things that those functions doesn't actually do any check. Most of those functions will just take the pointer you pass it to and just put it into the structure, and we'll check them later on. As we can see at the bottom of the C listing, you can see a TLS configure, and this is where every check for every configuration option is done. So this is quite different from the OCaml code, where there are types pretty much everywhere, and to get to these types you actually need to do yourself every error handling. Like you can't actually get an X509 authenticator A if your X509 chain is broken, whereas in the C example, well, can go bad at any point. So one of the big challenges with this binding is actually to bridge the programming styles. So like I said earlier, in libtls, configuration is mostly done through many setters on the configuration structs. The configuration is actually validated as a very late stage, that is when you apply the configuration to a context. And the OCaml libraries usually relies on types and then an argument, optional or named, to make it easier to actually not go wrong. So a simple solution that we can apply to this problem will pretty much looks like it. So we have all those configuration functions that we can just map to staging records for our configuration, where we actually take every one of those functions and try to make them fit inside it. So one of the upsides of this approach is that we can actually start to encode error scenarios to types. For example, something that could happen is that in our case, if we want to be sure that the users actually set everything we want, we just rely on types there with string options. We initialize the string to be just empty, to be just none, and then later on, when we check by applying and validating the configuration, if the thing is still none, then it means that something gone wrong. So it's actually making it pretty easier to check the configuration where in the C code they need to actually do a lot of pointer verification all the time, and it can get pretty cryptic to decipher of that. So that's a pretty simple solution to a few of these problems. One other problem we talked earlier about manual memory management and garbage collector is how to harmonize memory management. One of the many troubles you can get. So basically, in this case, you actually want to take a lot of OCaml values and give them to the C side. The main problem with that is that since the garbage collector actually have full control on the lifetime of these values, like for instance, at some point the garbage collector could decide that the value is not used anymore because you gave it to the C side. Since it doesn't know about it, it could just, well, remove the value and just free it. So that's the kind of problem you can encounter. Another kind of problem with the garbage collector is that if you want to, let's say, give back some pointer to an OCaml value, something that could happen is that the value could get moved during a GC compaction phase, and that will make the pointer invalid on the C side, so when they try to use it again, then you end up with a crash of the program. So a solution to that is actually already in C types with a few modules that will actually help you with that. So OCaml C types actually allow you to return a pointer to a block registered as a root inside OCaml's runtime, and then that holds the address to the value. But that's an address that won't move. So you can give it to the C side, and the actual value, the actual OCaml value is hidden inside this block. So you then fix the problem we talked earlier. Then if the value is moved during a GC compaction phase, the address itself is still valid, since you can just give back the address of the block you allocated earlier, and the C side won't even notice that the value moved. But you also need to manually manage this block, so you need to create it, set the new value, set the new value of the value if you update it, or just release the block, which is quite alright since we actually are binding to a C library, so manually handling it is not a problem. But you can still end up doing weird things like adding a call to malloc in your OCaml code, because we encountered a few fun issues where in libtls we had a function that basically wanted to read a certificate on the disk, possibly decrypt it, and then you return a buffer that the user needs to free using libtis free. So that's the kind of case where you can't do much except, well, calling malloc in your OCaml code, which is quite dirty, but well, you get used to it. So a quick note on the performances. So the performances numbers are actually pretty thin. libnq, we tried to measure the performances of libnq complicated name. I didn't choose it. libnq SBTLS is mostly around 70% as fast as libtls on comparable condition. So that means same configuration options, same cipher suite. We try to measure it mostly by measuring data transfer speed, so that is either inside HTTPD, OpenBSD HTTPD by just transferring files, or just writing some custom clients and servers and see how it went without the HTTPD overhead. So Yeah, the main problem I have with that number is it doesn't tell us actually a lot, because it tells more about what are the differences between OCaml TLS implementation and the libtls one, which is OpenSSL. So another number I try to measure is actually comparing libtqsb TLS with OCaml TLS, which was quite complicated because you're basically comparing a C program that calls through the FFI to an OCaml library, and then you try to compare it to some OCaml code that tries to do the same thing, but not quite. So overall, I measured around 10% of performance decrease between OCaml TLS and libtqsb TLS on a very naive implementation. The prototype we use right now isn't optimized in any way. It's very naive C-types code. So there is, I think, many possibilities of optimization. And that's pretty much the numbers we have. Yeah, around 10%, 15%, which isn't saying a lot. I should have added some nice graphics and numbers. I'm truly sorry about that. If you have more questions on it, we can talk about it later. And I think that's not pretty much it. So getting back on running the library into a system like you saw at the beginning of it, running the library within HTTPD, OpenBSD HTTPD. So our library runs within most components within the base OpenBSD system. So that is HTTPD, netcat, curl, FTP. So that is both client and server softwares. But a few things we've noticed while making it run within the software is that there are a few cases where there are behavior differences that you wouldn't actually expect. One nice catch like it will be when we were trying to run it inside HTTPD, we got caught off guard by the capabilities system for OpenBSD, which is through the pledge syscalls that allow a program to relinquish the access to a few syscalls, a few selected syscalls. So what happened basically is that at some point we were trying to read the certificate at a point where HTTPD has actually relinquished its access to the file system, to a part of the file system, so it couldn't read the certificate. And that's what, yeah, quite subtle, because that means that basically libtls was reading on the file system at another point, which was before validating the configuration, when in our library we were reading on the file system during the validation of the configuration, which is quite subtle, but yeah, I think that's kind of the thing that we need to watch out when trying to match the behaviors. It's not only about an interface, but also truly about matching the internal behavior. And I think that's it. So here is the GitHub repository for the library. If you have questions, I guess we can do it now.
Question?
So you gave the overall bulk performance numbers, but I think it's often important for networking applications is the kind of determinism of latencies. And I would think that would be a kind of barrier for adoption for C programmers for dealing with something with a managed runtime. And I'm curious if you have any kind of numbers of what happens to the latency distribution as opposed to just like the kind of average throughput when you go from the C implementation to the OCaml TLS one.
Yeah, that's actually something I really wanted to measure, but I didn't have quite enough time. Yeah, that's one of the things I was trying to say at first, which was like, yeah, we got a number showing basically OCaml TLS versus libtls, which has been done before, I think, in the first presentation of OCaml TLS. And that's something I like to do in the future if I have some time, trying to see first where the performances are distributed within libtqsb TLS. Like, does the call to the FFI are actually that costly for libtqsb TLS? I missed numbers on that. We'll probably try to work on that in the near future. But definitely, yeah, we'll publish something if I work on it.
Do you plan to propose this for integration into OpenBSD?
I think Anil has something to answer.
Yeah, this is a package. So in OpenBSD we expose TLS on H. So for Debian, for example, we can have a variant package which lets you choose between the OCaml TLS or the SO from the C package. So in OpenBSD it's in base, so it will not happen for a while, but in other systems that adopt the TLS, just be easy to do that. So I intend to try to build a Debian package for it. So if anyone wants to try it as well, let me know. before we submit a Debian package, these will get tested.
Thank you.
All right, other questions?
Why NQSB?
So if you ask me, that's not quite so broken, and the actual history behind it is not of my precise knowledge, so maybe David or Hannes can answer this question.
Because we had to submit an abstract and then something like the paper and it was like 50 minutes to take that and then well somebody came up with a catch game.
The rest is history.
The rest is
All right, any
Thank you.
questions? In that case, let's thank the speaker again.